In today's session, we will discuss some of the most important and frequently asked questions on the BJT and associated circuits like biasing techniques, common emitter, common base configurations, and amplifier analysis. All these question models are based on the previous year examinations of GATE, IES, ISRO, DRDO, Polytechnic Lecturers, and other state public sector unit examinations. Let's welcome to the channel Electronics Pariksha. Let's see the first question. A transistor works in three regions: cutoff, active, and saturation region, which is used in the digital logic gates the region works in. So here if you see the transistor output characteristics, we have three regions. As we have already seen, this is the output VI characteristics, this is VCE for a common emitter configuration, this is IC. This is basically the cutoff region. The cutoff region has VCE almost equals to VCC, and the flowing collector current will be very less, it is minimal. So that is the cutoff region. Means transistor is usually in an off region. In this is called cutoff region. Transistor acts like an open switch, so basically it is off. Then if you increase, this is means this characteristic is for IB is equals to very less, almost 0 microamperes. Okay, when the input current is 0 microamperes or approximately equal to 0 microamperes, there is no current that flows in the transistor circuit, in this common emitter. So then it is said to be in the cutoff region. Transistor acts like a open switch. Then you can ask, then what, when input current IB is equal to 0, what is this current IC? This is nothing but IC E naught. That is the reverse saturation current when transistor is connected in a common emitter configuration. This is nothing but IC naught, which is equal to 1 plus beta ICB naught. Okay. Now, if you slightly increase the input current, that is IB, then IC also starts increasing. This is the output VI characteristics when IB is normally increasing. Okay, this is for assume IB is equals to 1 microampere, 2 microamperes, 3 microamperes, and 5 microamperes. 4 and 5 it will is. So this entire thing is a linear region. This entire thing is nothing but this is the linear region. So this region is used for amplification purpose. This entire region is used for amplification purpose, where the output current IC, basically in this linear region, output current IC depends on input current. That is IB. So as IB varies, IC also varies. So as the input current changes, output current also changes. So this is nothing but this kind of operation is used in amplifiers. Okay, it is used in amplifiers. So all the amplifiers, power amplifiers, audio amplifiers, or video amplifiers, all these are configured in the linear region. So when input current, base current is goes beyond a certain value, means goes beyond this cutoff value, then a transistor will enter into saturation region. This entire thing is a saturation region. In this saturation region, IC flowing will be IC max. Maximum saturation current will flow. That is the maximum collector current this transistor can withdraw. That is the maximum collector current. So this is a, so in this it will act like a closed switch. In this mode, it will act like a closed switch. The input IB current, no more controls. Input IB, no more controls IC, the output IC. So if input IB base current is given beyond certain level, the IC will be driven to IC saturation. Saturation collector current will flow and transistor will be driven to saturation region. It will act like a closed switch. So the saturation and cutoff regions are nothing but the regions which make transistor to act like a closed switch or open switch respectively. So in the digital logic gates, we have only two logics. In digital, we have only two logics, that is 0 or 1. So based on these logics, we need the transistor to operate either in saturation region, that is closed switch, saturation region, which is nothing but closed switch, or cutoff region, that is open switch. So in digital, we have only two logics. There is no linear logic. There are no analog modes. So we need saturation region and cutoff region. That is 1 and 3. Answer is option C. We'll solve the next question. If alpha is 0.98, IC naught is 6 microamperes, IB is 100 microamperes for the transistor, then the value of IC is. So we have to write the IC equation, that is collector current is equals to beta IB plus 1 plus beta IC B naught. This is the collector current equation that we have. Okay, but given parameter is alpha, that is equals to 0.98. We have beta is equals to alpha divided by 1 minus alpha. So from this, we can calculate 0.98 divided by 1 minus 0.98. So beta is equals to 49. Substituting this value here, the collector current IC is nothing but beta is 49, the base current is 100 microamperes plus 1 plus beta is 50 and IC naught is 6 microamperes. So the collector current IC equal to 5.2 milliamps. So the answer is option D. Those who want the explanation how beta is equals to alpha divided by 1 minus alpha will see here. So this is basically the common base configuration. This is emitter, this is base, and this is collector. So here the collector current is nothing but collector current. Basically emitter current is equals to IB plus IC. So this base current will be less than 5% of the emitter current, whereas collector current is greater than 95%. Okay, so in the common base mode, the alpha is nothing but the amplification factor, current amplification factor. The output current is IC, the input current is IE. Alpha is equals to IC by IE. So collector current equation here will be alpha IE plus the small reverse current will be flowing between the base collector junction because the base collector junction will be reverse biased. Usually in amplifiers, input junction will be forward biased, output junction is reverse biased. So a small reverse current will flow across this junction. That is nothing but IC naught. This is a basic collector current equation for the common base amplifier. If you substitute here, alpha is equals to IE is equal emitter current is equals to IB plus IC naught. So if you solve this, IC is equals to IC minus alpha IC is equals to alpha IB plus IC naught. So here IC is equals to 1 minus alpha is equals to alpha IB plus IC naught. IC can be written as alpha divided by 1 minus alpha into IB plus 1 divided by 1 minus alpha is IC naught, which resembles to the collector current equation of common emitter. IC is equals to beta IB plus IC E naught. Here this is common emitter reverse current. So here now by comparing this, beta is equals to alpha divided by 1 minus alpha and IC E naught is equals to 1 plus beta into IC naught. Okay, hope you understood this comparison. We'll see the next question. In a circuit given below, assume that VCC is 15 volts. There are 4 Zener diodes, Z1, Z2, Z3 and Z4, identical Zener diodes with a breakdown voltage of 5 volt. R1 is equals to R4 is equals to 5 kilo ohm. This is 5 kilo ohm and this is 5 kilo ohm. R2, R3 is 10 kilo ohm. He's asking us to find out V out, the output voltage. So if you observe carefully, he's telling Q1 is off. So when Q1 is off, the current enters here and it will flow like this into this branch and into this branch. So if you apply nodal analysis here at this point, you will get the answer by applying nodal analysis. It's nothing but KCL. Here at this point, at the collector point, you will get VCC minus V naught divided by R1. That is the incoming current, which is equals to outgoing currents. V naught minus Zener diodes have the breakdown voltage of 5 volts divided by 10 kilo ohm plus V naught minus 5 divided by 10 kilo ohm. If you substitute VCC value here, it will be 15 volts. VCC is 15 volts. So now you can solve this equation. V naught minus 15 by R1 is nothing but 5 kilo ohm plus V naught minus 5 divided by 10 kilo ohm plus V out minus 5 divided by 10 kilo ohm is equal to 0. You will get 2 V out minus 30 plus V naught minus 5 plus V out minus 5 divided by 10 kilo ohm is equals to 0. So by solving this, we'll get 4 V out is equals to 40. Output voltage is equal to 10 volt. So the answer is option C. Like the video, share the video, and subscribe to the channel for better content and more videos. We'll see the next question. For 1 volt emitter bias, what is the RE if IE is 300 milliamps? So it's telling V emitter voltage is equals to emitter current multiplied by emitter resistance. So RE is nothing but VE divided by IE. Emitter voltage is 1 volt and this is 300 milliamps. So here the answer is 0.33 ohms. Option B. Next question. For the lower Q point of the operation of the diode, AC resistance is. See, the diode characteristics is like this. Till the cut-in voltage, the current will be very low. After the cut-in voltage, the current drastically increases. Okay. This is basically the diode characteristics. This is for 0.3 and this is for 0.7. This is 0.7, that is silicon diode. This is zero point 0.3, that is germanium diode. So generally a diode, he is telling low Q point. Low Q point in the sense the operation will be here. This is the low Q point operation. So in the low Q point operation, the diode resistance R, that is change in the diode voltage divided by the diode current, will be very small. Very high means the change in the voltage. This is diode current, this is diode voltage. The diode voltage divided by diode current will, this change is very high, very small. The change in the diode current is very small. For the lower voltages, so the resistance is usually high because here the diode resistance is inversely proportional to diode current. So answer is A. We'll see the next question. The reverse saturation current in the collector region of the transistor. See the reverse saturation current in the collector region. If you take in this particular thing, this is emitter, this is base, and this is a collector. The reverse saturation current is flowing in this direction because this junction is for reverse biased. The output junction is reverse biased, input junction is forward biased. So if you observe the reverse saturation current, this is nothing but a diode junction. So the current will be I naught e to the power of eta Vt e to the power of Vd, the junction voltage, divided by eta Vt minus 1. Here Vt is a thermal equivalent voltage. Vt is a thermal equivalent voltage which is directly proportional to temperature. Okay. So the reverse saturation current I naught is directly proportional to temperature. If you observe carefully. So the reverse saturation current in a collector region increases with temperature. If alpha is equals to 0.995, emitter current is 10 milliamps, IC naught is 0.5 microamps, then IC E naught is. We have already seen IC E naught. The reverse current in the common emitter configuration with input terminal open is equals to 1 plus beta times of IC naught. But here he has given alpha. We know that 1 plus beta can also be written as 1 minus alpha IC naught. So IC naught can be written as 1 divided by 1 minus 0.995 multiplied by 0.5 microamps. 100 microamperes. So answer is option A. If you see the next question, the current gain and voltage gain of the emitter follow a circuit in the given figure are. So output is here output is taken across the emitter, means input is given at the base, means it is a common collector amplifier. For common collector amplifier, the current gain gamma is equals to 1 plus beta, and voltage gain will be approximately equal to 1. So let's find out the current gain, that is 1 plus HFE, which is 1 plus 100, that is equals to 101. Whereas the voltage gain will be approximately equal to 1. So the options, if you observe carefully, option C will be the answer because it is 101, 0.9 and 16. If you see the next question, the collector to ground voltage is 20 volts. Which of the following is a proper? So he's telling the collector to ground voltage means here the output voltage. He's telling it is 20 volts, which is nothing but a VCC. So the output voltage, the collector to emitter ground voltage is equals to VCC. This happens when IC is equals to 0. When IC is equals to 0. If you see the equation, voltage equation, VCC is equals to VCE minus IC RC. This is the voltage equation that we have. He is telling VCC, VCE is equals to the output collector voltage. This is VCE, the collector emitter voltage, is equals to VCC. This happens when collector current is 0. RC cannot be 0 because it is a constant. So when collector current is 0, this situation happens. So the collector current, when it will be 0, we'll see the options. The collector emitter terminals are short circuited. When the collector emitter terminals are short circuited, IC is maximum and VCE is equal to 0. So this condition is not correct. When emitter to ground connection is open, he is telling emitter to ground connection is open. So in that case, the collector current or emitter current doesn't flow. So this condition is probably correct. Base resistor is open. So when base resistor is open, even in that case, the transistor will be in off condition, but transistor will be in off condition. But here, that is not possible because the base resistor is given as 47 kilo ohms. Clearly. So even this is not possible. The collector base terminal is short circuited. He is telling this and this are short circuited. Even in that case, the output voltage will not be equal to 20 volts. Then the current flows in this direction. So the output voltage is nothing but the base voltage. So it will not be 20 volts, it will be the base voltage. Base voltage is nothing but this base to emitter voltage. So even this is not correct. So the answer is option B. Like the video, share the video, and subscribe to the channel for better content and more videos. In the circuit shown below, the silicon NPN transistor Q has very high value of beta. The required value of R2 to produce IC is equals to 1 milliamp is. So if you observe it here, the current gain is very high. He's telling beta is infinite. So for this case, the collector current and emitter current will be equal. So here, the collector current IC is equals to 1 milliamp, which is equals to the same emitter current. So the voltage across emitter resistance is IE into R. Which is equals to emitter current is 1 milliamp, resistance is emitter resistance is 500, which is equals to 0.5 volts. So the voltage across emitter resistance is 0.5 volts. So if you apply Kirchhoff voltage law in this loop, the voltage across R2 must be equal to the voltage across R2, VR2 is nothing but 0.7 volts base to emitter junction voltage plus 0.5, which is equals to 1.2 volts. That is the voltage across R2. So now you should apply the Thevenin's theorem. Now, if you take a Kirchhoff voltage law here, by applying like this, you will get VCC is nothing but voltage across R1 plus voltage across R2. Okay. Now, the voltage across R2 is, the voltage across R2 can be given as VCC divided by R1 plus R2, that is the current flowing through R2 resistance, multiplied by R2 resistance. So voltage across R2 is nothing but 1.2 volts, VCC is 3 volts, R1 is 60 kilo ohms plus R2 multiplied by R2. By solving this, R2 is equals to 40 kilo ohm. So the answer is 40 kilo ohms. In a transistor amplifier, VCE is equals to, see, this is the emitter, this is the base, and this is the collector. VCE is equals to VCB, the collector base junction voltage, plus the base emitter voltage. So VCE can be given as VCB plus VBE. The answer is option A. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.